Hi, today I'll be going through question 3 of the PHYS 457 practice midterm. Now, question 3 asks, nichrome is a poor conductor and is used to make small electrical heaters in a laboratory and vacuum systems. A piece of nichrome wire has a cross-section of radius A and length L. Nichrome's resistivity is constant over a very wide range, and we'll call that constant rho. The right end of this end of the wire is held at V is equal to V naught, and the other end of the wire is held at V is equal to 0. You take the z-hat direction as going from V is equal to 0, as going from V is equal to 0 to V is equal to V naught. And then the s-hat direction just points outward from the center of the wire, and the phi-hat direction you can determine using the normal right-hand rule. Okay, so there are many parts to this question, and I'll be going through first part A, which asks, in terms of the parameters given, what is the current flowing in the wire? So there are two ways of tackling this problem. One is slightly simpler and is slightly simpler than the other, but I'll be going through both. So the simplest way to think of this problem is to just think of the very basic Ohm's law. So V is equal to IR. Although in this case you're not really given R. Well, actually you are given R explicitly. You can get it from the resistivity. Now resistivity, and you can get this from the resistivity, you can get resistance from the resistivity because resistivity of a material is defined as the area of the material, the cross-sectional area over the material divided by the length of it times the resistance. A little rearranging, and you can rewrite this as L A rho is equal to R. But then on top of that, we also know that the area, the cross-sectional area of this is pi a squared, since a is the radius. So R overall is just L over pi a squared and times rho. And then from this, you can immediately get the voltage. You can immediately get the voltage to be the voltage in terms of the stuff given. And we also know that this is equal to V naught. That this is equal to V naught because that's where you have your V defined. So L is therefore equal to pi a squared rho. And then from this, current just becomes I is equal to pi a squared over L rho, and this is V naught. And with that, this part, this question is finished. Okay, so leaving off from where we last left off, I'm going to go through the second way you can solve this problem. So, assuming you don't know that the definition of rho, what the definition of rho is, there's also another way of going about this problem that starts from the other form of Ohm's law, which is given as J is equal to sigma times E. Now, we know that sigma is by definition the inverse of resistivity. So we can use this fact to get that E is equal to rho J. Okay, we have this electric field which is equal to some constant of resistivity times the current density in this wire. So do we know these quantities? As it turns out, we do, because we know that, because for this case, the E field is simply the voltage over the length of wire. So in this case, it's the negative of the voltage because, and it's the negative of the voltage, because we're going from the region of high potential, V is equal to V naught, to the region of no potential, V is equal to 0. So just for reference, I'm going to draw this vector representing E, the direction of the electric field. And top of that, we also know what current density is. Current density is defined as I over A, and then some normal vector, which in this case is going to be Z hat. Now, we already know what the area of this cross-sectional area of this is, and that's pi a, simply pi a squared. So altogether, our expression that we have, just gonna demarcate that here. The expression that we have for our current density is I over pi a squared times the Z hat component. Now, if you want to get the if you want to get the magnitude of the current, then this just becomes, by this point, it's just algebra. So you just rearrange, and you find that V naught is equal to rho over L times pi a squared, and this is what? Yeah, V naught. Okay, let me just double check. So that is over there, pi a squared, V naught. And so yeah, with that, we have that the current, this is the magnitude of the current, and we already know from the sign of this that the current is actually parallel to the E field. So we so that, and with that, this problem is solved. Okay, so we finished part A, and from part A, which asked us, in terms of the parameters given, what is the current flowing in the wire, we determined that the current flowing through the wire is given by this expression right here. Now, the second question, or the second part, part B, asks, maintaining this voltage difference requires a certain amount of power. How much power does it take in terms of the parameters given? So, well, first off, before we answer this question, we have to answer another question. Well, what is power? Well, power is defined as is equal to IV, and we also know from Ohm's law that V is equal to IR. So, yeah. So this is also equal to I squared over the resistance. So we actually already know that we already know trivially that I is equal to this, but we also know what the resistivity is, because this term right here looks similar to Ohm's law, and you can write it as, alternatively, as V naught over R. So this is actually our 1 over R term. So with that, established, we can now go forth and write that the power flowing through our wire is given by, here, let's just this, V naught over R, all squared, times R. These two R's right here this R right here cancels with the R right here, and this leaves us with V naught squared over R, which in our 1 over R term is just this term right here. And so And so we're left, and so we are left with power is equal to pi a squared over rho L times V naught squared. And with that, this problem is finished.